Thank you for introducing me. So I'm Mariano Graziano. I'm a security researcher for Cisco. And today this talk is about a framework to detect and prevent any kind of spraying attacks. This is a joint work between University of Milano, between Cisco and Eurecom in France. So let's start with the definition of spraying. What is spraying? So spraying is a generic and common payload delivery technique that has been specifically designed with the goal to bypass the address space layout randomization that is an operating system protection to randomize the base address of the code and libraries. So over the years, security researchers have shown how to spray the heap, how to spray the kernel pools, or how to spray the just-in-time compiler pages. And over the years, basically, we know how to spray this memory region, but we can also categorize spraying depending on how the attacker is spraying, okay? So for historical reasons, the first method is the so-called traditional code-based spraying, okay? In this case, the scenario is that the operating system has the ASLR, so the address space layout randomization that is enabled, but the data execution prevention is either disabled or not supported. Okay, nowadays it is not so common, but for historical reasons, I have to mention also this approach. So in this case, anyway, when an ASLR is in place, the attacker needs to guess or anyway know the address of its payload, okay? So in order to increase the probability of success of the attack, one of the possible ways is to fill the memory of the target application with hundreds of thousands of copies of the payload that in this case is the shell code, okay? So then another possible case is the so-called JIT spraying. In this case, the idea is that the attacker wants to bypass both SLR and data execution prevention. In this way, in this case, the attacker basically is using the executable pages that are generating on the fly by the just-in-time compiler. Then for the case of data spraying and then for the stack pivoting, the main idea in this case is that, again, okay, the attacker wants to bypass both SLR and DEP, but in this case, it fills the memory with data. But in this case, data is in the form of ROP chain, so we have hundreds of thousands of copies of the same ROP chain. Then one of the first gadgets of this ROP chain perform the so-called pivoting. So this means that the stack pointer is changing 2 points to the sprayed data, okay? So in the last decade, the spraying phenomenon has been studied a lot by different researchers and from different perspectives. Now I'm going to talk a little bit about the related work for the defensive solutions. We have a couple of good papers about possible defensive solutions for the heap spraying. For instance, we have nozzle, we have a bubble, that are different approaches, but all these approaches, basically they are or application specific, so they just work, for instance, for one specific browser, or sometimes they only work for a specific JavaScript engine. Then we have also a couple of good and interesting papers about the JIT spraying, like JITsec or JIT Defender, lobotomy. And we have also here some browser developers that, like in another talk yesterday at USENIX, they show that we have like the code blinding or the NOP insertions in the browser. And anyway, all these approaches have been bypassed by motivated attacker, or again, they are really application specific, like they work only for Internet Explorer. Or even if they are more comprehensive, they just solve one instance of the spraying problem, like in this case, the JIT spraying. Then we have the problem of that we have some defensive solutions for data spraying. We have some companies that propose, like Microsoft, that propose Emmet. Emmet is a more generic solution in order to harden applications. And among the other things, have a really interesting feature that is the anti-pivoting. Then we have, again, some solution proposed by some browser developers, like the isolated heap or the delayed free, that anyway, they hinder the browser exploitation, in which the spraying is one of the steps. But again, these solutions are either application-specific, they work only for a browser, or they solve only a single instance of the spraying problem. So at this point, it should be quite clear that we need a kind of solution that is able to cope with all the possible spraying implementations. So what we would like is to have a comprehensive, scalable solution that can defeat any form of sprayings. And ideally, should be also operating system agnostic, so it can work transparently both with Linux and, for instance, Windows. So at the first sight, if we want to design such a system, such as spraying a defensive mechanism, the design at the first sight, it seems really simple. Because if we think about the spraying definition, okay, the first characteristic that's come up in our mind is that when an attacker performs spraying, it basically is allocating a large amount of memory in a small amount of time. So mistakenly, one can think that we can perform a really basic heuristics to detect such attacks. And if we look at these graphs, basically we have in green and in red the behavior of some normal browser activities, like we have a user that is browsing like Google Maps, YouTube, and another user that has other tabs open and is browsing like on news website. And here we have the memory behavior. Then we have in gray the attacks or the spraying attacks with a default exploit taken from the default configuration from Metasploit. And we can clearly see that the behavior is completely different, and we have a large amount of memory allocated in a small amount of time. So we have to keep in mind that we cannot design also such a system with such a simple heuristics because the attacker controls the two important parameters. The attacker can control the size of the allocated memory, and the attacker can control the speed, so the time of the allocation. So a motivated attacker can mimic basically the behavior of a benign application, and this is what we see here. Basically, we can mimic the normal browsing activities. So we need a way to create a more complex system. Okay, so we try to list some important goals to define such an important system. So the first goal should be to have an independent to have a system that is completely independent from the memory allocator. So in this way, we can plug our system to any kind of application, ranging from, I don't know, a browser to a PDF viewer. Then we need a system that is operating system agnostic, so can work, again, transparently on Windows and Mac OS X. Then we want a system that it's modular, because we want to plug many plugins that implement some heuristics to detect the different instances of spraying. And last but not least, we want a system that has a low overhead, because we want to deploy it on a real system machine, or at least the overhead has to be reasonable compared to other hypervisor solutions. So this is more or less the architecture of the system that we design. So let's imagine that someone is visiting a website that can be either malicious or benign. But anyway, the important part is that at a given point there will be some kind of allocation, okay? So this allocation is generally through an API, then it's translated in a system call, and then it's going down to the kernel up to the page tables. At this point, our system that is hypervisor-based is able to intercept this memory request, and this memory request is forwarded to the first component of our system that is called the memory tracer. Then when a given memory threshold is reached, the memory tracer component basically activates the second component, that is the attack detector, that is the component in charge of detecting possible spraying attempts. Now I will talk in detail about each component, so I will talk first about the memory tracer and then about the attack detector. So in order to understand the semantic of the memory operations in the guest operating system, our framework needs to monitor all the memory operations that happens on the paging structures of the monitored application. This is possible thanks to a feature provided by the Intel hardware system virtualization that is called the extended page table, in short, EPT. So in order to understand then the nature of these operations, these kind of operations are like the creation, the modification of the elimination of a memory page. In order to understand the nature of this operation, we need, because we want to know if these memory operations is touching directly the paging structure or is creating like a normal new memory page. Like we can see in this picture, our framework basically is checking the page directory entries and the page table entries. In particular, we check the bit permissions in order to understand if the page has been created, modified, or eliminated. And in order to understand if the memory operation is happening on the paging structure itself, we monitor the page directory. If the operation instead is just creating a page, a normal memory page, we check the page tables entries. Then, as I said before, if our system basically monitors all the paging structure. But if we do that for the system-wide, for the entire operating system, or we do it for multiple applications at the same time, during our experiments, we notice a huge overhead. Okay? And this overhead is somehow problematic because one of our goals is to have a lower or at least a reasonable overhead. Okay? So we try to investigate this issue. And what we notice is that even if we are monitoring a single process, what we expect is that we only notice the memory violation on the paging structure only for that particular process. But actually, we notice that the kernel at the same time is modifying the paging structures also of other processes. So what we want, so first of all, this is something that we noticed. So the first thing to do is to try to measure this problem that we call the interference problem. So the first experiments that we did was to measure the overhead for a single process. In this case, we choose Internet Explorer 10. And the overhead in this case was 22%, okay? Then we try to measure, again, the overhead for the same application, but at the same time we were monitoring other two additional applications, like Acrobat Reader and Firefox. And in this case, the overhead for the application is jumping from 22 to 63, okay? So basically we are increasing a lot, it's increasing a lot, the overhead, and this is something that we need to solve. So we brainstorming a lot, and we come up with a possible solution that we call the Micro-Virtualization. That is the main contribution of this research. So the main idea of Micro-Virtualization is to create a memory sandbox for every monitored application. So more in details, Micro-Virtualization is based on the Intel hardware-assisted virtualization features, the VTX, and in particular, it heavily relies on the extended page tables feature. So at the process creation, our system basically selects a set of physical pages that are related to the paging structures, and we monitor only these particular pages when the process is actually running. How this is possible? This is possible thanks to the so-called extended page table pointer. So at every process which basically we change this pointer to point to the set of physical pages that we want to monitor. So this means that we create an APT pointer for every application that we want to monitor. So now we will talk about the second component that is called the Attack Detector. This component is activated only when we reach a certain activation threshold. And it's important also to notice that, this detector is implemented with many plugins, okay, on top of the memory tracing system. So anyone then can plug its own plugins and implement its own heuristics. So the first plugin that we implemented is called the Malicious Code Detector. Again, here the scenario is that the operating system has ASLR that is enabled, but DEP is not activated. So the idea here is that we randomly scan the allocated pages so far for that particular application and we look for evidences of shellcodes. There are several approaches in the literature, like a paper from AXAC 2010 or a USENIX security paper from 2011. The important part is that we can port these heuristics to our own plugin on top of our memory tracing system. Then another plugin that we implemented is called the self-unpacking shellcode detector. So basically here we want to detect any possible unpacking behavior. So this means the common unpacking behavior is that when you write a page and then you execute it. So basically we search on the memory pages this particular behavior of write and then execute, and we implement these heuristics. It is, again, is not an idea, it's taken from a paper from AXAC 2007. Then for the data, we have another plugin that is another use case for our framework that implements a data spraying detector. Again, in this case, what we want to do is we scan the memory pages allocated so far for that particular application, and we implemented an heuristic that checks the frequency of the code pointers. And, but again, we can port also other previous approaches as a form of plugin in order to detect data spraying. So now let's talk about the experiments that we did. The first experiment is that we did perform is to measure the overhead of the first component, that is the memory tracer, that is the only component that is always active. So what we did is we used the stress suite, that is a benchmark suite that basically stress the allocation and deallocation. And in particular, this application create a program that simulates a lot of allocation and deallocation, and we did it for Windows 7 and Linux 3.2. And with an allocation deallocation speed of, on average, 8 megabytes every 2 seconds. We measured the overhead, and we had for Windows 7 24% and for Linux 25%, only for the memory tracer. But this is the worst case because we are using a stressing suite. Then another experiment that we did is basically to measure the overhead for our system by changing the activation threshold. That is that threshold that is in charge of activating the second component that is performing basically the checks for the possible spraying attempts. So we start with a really conservative threshold of 100 megabytes, and we went up to a threshold of 400 megabytes. As expected, I mean, the lower is the activation threshold, the higher it's the overhead, because we have more switches between the memory tracer, of course, and the attack detector. Then we did a couple of experiments to measure the effectiveness of our system. So in this case, we took 6 different attacks, 6 different real exploits that we carefully choose to be representative for the possible spraying implementation. So in fact, we ran from some plain shellcode spraying to the data spraying with, of course, with ROP. And then we also choose different applications, like browser, like Internet Explorer or Firefox, to PDF reader, and up to Flash player. In all the cases, our system was able to detect and prevent the spraying behavior. Then another experiment that we perform is to assess the accuracy of our system. So in this case, we took 1,000 of benign PDF and then 1,000 of malicious PDF. We configure our system with a really conservative threshold of 150 megabytes. And for the case of the PDF, we were monitoring only the PDF viewer. In this case, our framework, Graffiti, was able to detect with any false positive and any false negative all the attacks. And then we did the same experiment by monitoring a browser with the same conservative threshold, and we visit the top 1,000 Alexa website. And here we were expecting is, of course, to not find any possible attacks, and this is what happened. So we didn't have, again, any false positive or any false negative. Then as a final experiment, given the fact that we want to deploy a real system on a real user machine, so we install our system on 2 different machines, and we asked two users to use our system for 1 week for their daily activities. So they were using, on average, 8 to 10 hours per day our system. Specifically, we configured our system to monitor the browser that these users were using, that was Internet Explorer 8, on their operating system that was Windows 7. And we set up a really conservative threshold of 150 megabytes. And also in this case, for the Attack Detector, we activated all the 3 plugins that I explained before. Then after 1 week, we check the results. So the users visited more than 400 different websites. The Attack Detector has been activated more than 50 times with an average of 8 times per day. Interestingly, we noticed, and surprisingly, we noticed that we had 12 alerts on pages that at the end were benign, so these are real, false positives. And we investigated this issue, and we discovered that it was related to the data spraying detector plugin. And then we performed again the experiment by improving this plugin. The plugin was only checking the code, the frequency of the code pointers. We perform an additional check if these code pointers basically contains a ROP gadget. And in this way, we filter out these false positives. So the important part here is to understand that the plugins can be improved a lot. So as a conclusion, here I present Graffiti, that is this framework that should be the first efficient and comprehensive solution to defeat any kind of possible spraying implementation. I described the main idea of the micro-virtualization. So in order to create this kind of memory sandbox for a specific application. And then most importantly, we are releasing our tools as open source, and you can download it from this website. Feel free to try it, send us your pull request, or create your own plugins on top of our memory tracer. And if you do it, please let's stay in touch. So that's all for me. Thanks for your attention, and I'm open to any questions.
Note takers? I have one for you. It seems to me that you're equating a process in an application in your framework. But some of the browsers, I might have misunderstood this, but browsers like Chrome, they have this multi-process architecture, which seems to me that might look like multiple applications to you. And if so, could an adversary try to distribute his spraying attempt over multiple tabs, which would have their own processes and thereby go undetected?
Yeah, for Chrome, the situation should be, a little bit more different, also with also more modern browsers, because now every tab is a single process. So probably you should have to configure the system for these different processes. So this means that you, with micro-virtualization, you are protecting all the different tabs. But then the attack again is on the single tab. And then, there is the sandbox. So now all the modern browsers have a sandbox, a memory sandbox. So then you have to escape from the sandbox, and then you have another attack. So now is chaining more attacks together in order to escape and then run code inside the operating system.
I understand, but let's say that for a given amount of data, you have X% a success rate. If I then spray a tenth of that in 10 tabs, I might go below your threshold, but viewed across the tabs, the same likelihood of succeeding with my exploit.
But every tab is a different process, right?
Yes, but only one of them has to successfully exploit the process.
Yeah, but okay, yeah, of course. But I can tune, you can tune the interesting part of our system is that you can tune the threshold, right? So basically, if you put a lower, if you are really, really paranoid, and in the wild there are these kind of attacks, what you can do is to lower the threshold. So in this way, you have a little bit more higher overhead, of course, but you are protected.
Right.
Just kind of a follow-up on that. If the overhead that required using separate EPTP pointers for every process had to do with the shared pages between processes, wouldn't a browser that's opening or that's running every tab in a separate process reintroduce that overhead even with having a separate EPTP for every tab?
No, what we noticed is that if we were using only one APT, we had this huge overhead. So we tried to debug and investigate a lot this issue, and is probably related to the shared pages, but most interesting probably is something related to some optimization on the memory subsystem inside the kernel, okay? So, and then what we noticed is that if we were creating more APT for the different processes that we are monitoring, we were filtering out the huge part of this overhead that so probably was related to some shared pages between the user application and the kernel. Mm-hmm. But it's something that, for the future work, we are still investigating because, it's something that for us was just a shared page, okay? But then you were asking about, your question was in 2 points, right? One about the overhead of the interference problem, and the other part, can you rephrase, please?
Is so there's still going to be, it seems like the kernel would still have to do a lot of extra work that would get caught on a forked or a copied process from the original browser process, and it seems like that work would be the same as the overhead that you would see using just the single EPTP, because it's the same page table entries that have to get amended because they were copy on write and now they're being changed for the new process.
Yeah, that's one of the points. It's something that we are investigating for the future work. What we're trying to do is just to do an APT only for the kernel and monitor what's only happening for the kernel, because what we don't have clear at this point is, why sometimes the overhead is getting so high, okay? So it's something that we are, actively investigating. And if you probably will check out the GitHub, hopefully we're going to commit something soon.
Okay. I have another question. So the VM func instruction that allows a guest to request a specific EPTP, I believe that runs in ring 3, so it's an unprivileged command. Did you do any tests to see if you had a piece of shell code that just kind of sprayed VM func? Would it crash the...
That's an interesting point. No, we didn't do it, but it is something, that could be really interesting to test.
Just to see what happens. What part of the system crashes when you do that?
Yeah, most probably, yeah. Thanks for your point. It's something that we're going to do.
All right, let's close the session by thanking all the speakers one last time.